Привет. Кстати, мы в прямом эфире. А, вот вы. А?
Настя сказала, что не работает.
Не работает?
Можно поздороваться?
Да, выходите. Ага. Да, Елена. Дима дарит. Прошенька, ты можешь спросить, что у моей мамы, допустим, работает ли ссылка?
Настя, это такая ссылка.
А?
Работает.
Работает? Да. А, все окей.
Снимал хорошо.
Je pense que Julie voudrait faire aucune demande, mais pas ensemble. Mais voilà.
Oui, on va voir.
Voilà. Bah, au début, je pense que c'est ton intérêt d'être le plus proche à l'ordinateur, tu as porte-parole. Moi, je vais le cacher.
Oui, c'est ça.
Parce qu'elle va commencer, c'est elle qui dit.
On est ça pour l'instant, mais on est sur
Voilà, je Qu'est-ce que tu m'as président, on espère que ça sera comme ça. En fait, si par exemple, on ne peut pas l'attendre pour telle raison, on fait dynamique au maximum, et c'est toi qui trouve la étrangère. Au pire.
À ce moment-là, peut-être que tu peux déconnecter ton chat.
Oui,
Tu peux utiliser le
annoncer
si tu veux, mais
porte-parole
je sais
du
pas si...
président. Donc, comme ça. Alors, je n'ai pas encore trouvé Jean-Pierre Colonna. C'est ça que je cherche maintenant. Ah, tu veux dire, c'est normal? Non.
Le type que je fais l'arrobase.
Il est écrit comment Jean-Pierre? Comme Jean-Pierre Colonna, je sais pas si c'est pas ça.
Je suis vraiment alors.
précédent.
Ah oui, peut-être qu'on a eu moins ça peut automatiquement.
C'est lui qui s'est passé. Qu'est-ce que tu dis, j'ai dit qu'on a eu un coup pour la semaine. Pardon. Une fois que la thèse est passée. Ouais, une fois que la thèse est passée. Le problème, c'est que c'est la thèse en fait. Ça dépend. Oui, la chose sérieuse, par contre, c'est oui, encore, quand même le second dépôt à faire. Je suis encore dans l'état où je focus sur la thèse, dans le L'idée, est-ce que tu as une idée de ce que tu as utilisé cette orchestre? Est-ce que tu sais où est le bouton pour faire descendre? Non, ça c'est les éclairages.
Et il y a des gros boutons en dessous?
C'est l'éclairage sur ça.
Ouais.
Et il est d'accord qu'il est pas manuel.
Est-ce que donc là, Jean-Pierre, on a
Ah, mais il s'enfonce pas. Ah, je pense.
fais attention à ça.
Je vais essayer.
Ah, you have Jean-Pierre,
Yes, whatever.
Good morning.
Finalement, la solution la plus simple, des fois, la bonne technique. On avait avec comme ça.
So, dear ladies and gentlemen, just preliminary announcement. We had some unexpected issue because our president of jury yesterday has received a positive test for COVID. So, president of jury will be on Zoom. It's him we are waiting now. And we will have porte-parole, the president of jury, so the person who will translate his words if there is a problem. It's Dr. Georgy. Okay, so we have president who will join us now, hopefully. And we have porte-parole.
Can I make a test of the sound for the
Georgy?
Can you make sure that all the jury hear the room well when you speak?
Okay, so can you hear us?
But you should stand like when you will be speaking.
Sure.
Please make it just here. So, just for you, I have just announced that you are president of jury. Can you hear me? Wave your hand if you can. Ah, you cannot.
Yes.
Okay,
Wonderful.
cool.
Thank you.
Cool. And so, Olivier Boitella, ici présent, he will be porte-parole du président de jury if there is any problem. But by the definition, we hope that there will no problem. Can you hear me from here, from the place of jury, please?
No, not very well.
Can you hear me now? Can you hear me now?
Yeah, it's okay, but as long as you don't
Okay, can you hear me now? And now?
that's better.
That's better. In this case, I suggest a specific. defense. So guys, when you will put the questions, you simply will stand here, okay? Thank you.
So everyone can hear me, right? And everyone can see the presentation.
Yes, yes.
Okay, perfect.
Okay, so I think that this is my begin. I assume that everyone is there and everyone is comfortable. So I'll begin by introducing members. So we'll start with two rapporteurs. Vasco Guerra, the Instituto Superior Técnico from Portugal, with on Zoom. Morning. Yeah. We have Lode from the Université de Toulouse, France, who is in the room, I believe.
Yes.
I suspect he is smiling and waving.
Yeah, in the mask.
Olivier Goitela from the LPP and Corporate Technique.
Yes.
By the way, please, Olivier. Giampiero Corona from the University of Bari, Italy. On Zoom, the comfort of his chair. And Giorgio Di Lecce, sorry if I mispronounced that.
Oh, no, it's very good. Thank you. Good morning, everybody.
I'm Eric Johnson from the LPSCM at the Pokrovskiy. And Svetlana Pokrovskiy is, of course, the supervisor of Georgy Pokrovskiy.
Yes, here.
Now, hello, good morning, says Svetlana.
Morning.
Good morning. And so now, Georgy, you have between 45 minutes to an hour to present your work. And we will begin the deliberation discussion. You have the floor. I believe that your presentation is in, you can see your next slides.
Okay.
If you click on paramètres d'affichage in the top there,
Okay. Could you see?
you can see it, but you also see the upcoming slide in your notes.
Sorry.
You click on paramètres d'affichage.
Okay.
It's good.
So now it's good.
Perfect. Thank you.
Okay. Hello everyone, dear members of jury. I'm glad to see you on my presentation of my PhD work, which is dedicated to the problem of dissociation of carbon dioxide at high levels of specific deposited energy and high levels of the reduced electric field. My presentation will be separated onto, sorry, just
You have to click back on your slide.
okay. Okay. So my presentation will be divided into 6 main parts. In the first part, I'm going to talk about the state of the art of the problem of the plasma-assisted conversion of carbon dioxide. And we will understand why a nanosecond capillary discharge can be a very powerful instrument for the conversion of carbon dioxide. In the second part, I'm going to talk about the experimental setups and methods which were used in the experiments. We're going to discuss the advantages and disadvantages. The third part will be mainly dedicated to the experiments. We will discuss the electric characteristics, the temperature, the optical emission spectra, and some other important parameters. The fourth part is the zero-D numerical modeling. It is important to apply it since a numerical modeling of the discharge is an instrument which can allow to understand which processes are responsible for the plasma chemistry at nanosecond timescale. The fifth part will be the so-called the part of application, since we will learn how efficient and how useful is a nanosecond capillary discharge in some applications. And finally, the sixth part will be dedicated to the general conclusions of the presentation. I'm starting now with the introduction part. First of all, the problem of the plasma-assisted conversion of carbon dioxide is very important, since CO2 is one of the most essential greenhouse gases in our atmosphere, and during the last decades the anthropogenic outcome of the CO2 increases. And the most part of the country has signed the Paris Agreement, which is used for the mitigation of the increase of the global temperature. Another interesting point for the plasma-assisted conversion of carbon dioxide is the fact that the Martian atmosphere mostly consists on CO2, and it is possible to synthesize the propellant and oxygen directly from the Martian atmosphere. Plasma-assisted conversion of carbon dioxide is the object of scientific interest since the middle of the previous century. The most conventional mechanism of CO2 conversion by plasma is the so-called vibration excitation. What happens? If an electron which is accelerated by the electric field collides with the CO2 molecule, it can enhance their vibrations. Then, when two vibrationally excited molecules collide with each other, they can exchange the vibrational quanta and come on the vibrational ladder. At some point, a CO2 molecule can exceed the dissociation threshold and to dissociate. This is the mechanism which takes place at relatively low electric fields, between 10 and 100,000. But it's not the only mechanism which is possible for the CO2 dissociation. It can be possible to dissociate it via the electronic degrees of freedom, and this process is dominant at the relatively high electric fields, higher than 100,000. The recent experiments, for example, in glow discharge, made in the teams of Olivier Guaitella and Vasco Guerra, for example, in the glow discharge, has seen that the glow discharge is quite a good instrument, especially at low pressures, since it provides the very good dissociation fraction at second time scale. However, there is a problem that there is a heating of the gas. The gas heating mitigates the dissociation of CO2 since it facilitates the back oxidation of dissociation products back to CO2. The glow discharge is a border instrument in the term that it combines both vibrational excitation and electronic excitation. But it is interesting what will happen after. What will happen if we increase the reduced electric field even more. And the nanosecond discharge can be very interesting instrument. And if we ignite a nanosecond capillary discharge, we will have a high value of specific deposited energy. The previous experiments in the nanosecond capillary discharge were done in air, and it can be seen that almost 100% of oxygen dissociation in air was observed. What happens? At nanosecond time scale, the nitrogen was excited by electronic impact up to N2A and N2B states. Then, these states were acted as a reservoir of additional energy, and they could dissociate oxygen at nanosecond time scale, more precisely at sub-microsecond time scale. And then this reaction has an energy defect, and this energy defect comes to the translational degrees of freedom. And it can be seen that the measurements of the gas temperature have revealed the fact that the temperature at nanosecond time scale is as high as 2000 kelvins. A similar experiment in nanosecond capillary discharge was done in the group of Georgy and again it can be seen that there is a significant increase of temperature and a conversion of CO2 at microsecond time scale. We have understood that a nanosecond capillary discharge can be very interesting instruments which can enhance the knowledge of the problem of the plasma system conversion of carbon dioxide, and we are ready to formulate the problem of the current thesis. First of all, it is necessary to ignite the discharge. Second, it is essential to measure its electric characteristics, such as the reduced electric field, the specific deposited energy, and since the electron density is the parameter which describes the plasma chemistry at nanosecond time scale, it is important to measure its temporal and spatial profile. Then, it is important to record the optical characteristics, since it is a very powerful instrument which allows to understand which species are abundant. It is necessary to conduct time-resolved temperature measurements in order to understand whether we have the effect of fast-gas heating or not. Then, it is important to apply the 0D numerical modeling. In fact, it will help us to understand which processes are responsible for the development of the discharge. And finally, the FTIR measurement of steady-state dissociation fraction and energy efficiency will help us to learn the answer for the question whether a nanosecond capillary discharge is the powerful instrument or not. If it's not sufficiently powerful, what can be enhanced? I'm now going about to talk about the experimental setups and methods. First of all, it is important that there were two main setups used in the experiments: the so-called thin capillary and the FTIR capillary. The thin capillary was used for the most part of the measurements, and the FTIR capillary was used mainly for the measurements of the steady-state values of CO2 dissociation degree and its energy efficiency. As for the thin capillary, its main advantage was the fact that it was possible to measure the electric field by the capacitive probe. The capacitive probe is a very powerful instrument since it provides a very good temporal resolution. In particular, it is possible to resolve a fast ionization wave propagating from the high voltage electrode to the low voltage one. It is important that both electrodes were connected to coaxial cables. In fact, the measurement of the electric field by the capacitive probe was not the only way of measurements of the electric field. It was possible to estimate and at some point measure it by a pair of back current shunts which were inserted in coaxial cables and connected to the oscilloscope. In its turn, it was registering the propagation of the high voltage signal in the coaxial cable. The FTIR was quite different from the thin capillary, since it had the only one cable. Its central wire was connected to the high voltage electrode, and its shielding was connected to the ground. Such a configuration provided the most possible amount of specific deposited energy, but the disadvantage of this configuration was the fact that it wasn't possible to measure the propagation of the electric field of the fast ionization wave by the capacitive probe. And it was only possible to estimate it by the only back current shunt which was inserted in the high voltage cable. Hereinafter we are going to take into account that there were 3 high voltage pulses. And now I'm going to explain their origin. The pulse which is designated by the number 1 is the incident pulse. The incident pulse which comes from the high voltage generator to the discharge tube. And then the pulse number 2, this is the pulse which is reflected from the discharge tube. And this is the pulse which is captured by the back current shunt number 2, and this is the transmitted current. We have the incident, reflected, and the transmitted pulse. Then, the pulse which is reflected from the discharge tube goes to the generator, reflects from it, and then generates another triad of the pulse, another incident, reflected, and the transmitted pulse. Finally, the same story repeats for the third triad of pulse. It is essential that the consequent pulses were negligible because of the construction of the generator. So far, we have briefly discussed the setups, and now we're going to talk about the measurements and the techniques which were used in the measurements. We're going to talk how exactly the reduced electric field and the electric currents were measured, as well as the specific deposited energy. as it has been said, these are the parameters which describes the behavior of the discharge. Then, the spatial profile of the electron density, which was related to the emission of N to C, was essential to measure it. In fact, the nitrogen was inserted to CO2 as a small admixture. Then, it is important to measure the temporal profile of the electron density, to measure then the gas temperature, which is related to the rotational temperature of N to C, whereas whereas N2 was inserted again as a small admixture to the CO2. And we're going to talk about the optical emission spectroscopy. As a reminder, we have a tribe of pulse which form a high voltage pulse. We have the incident, reflected, and the transmitted pulse. And then it's possible to synchronize them. As soon as the pulses are synchronized, it is possible to estimate the electric field as a function of time, simply by finding the difference of potentials on the high voltage electrode and the low voltage electrodes, and to divide it onto the interelectrode distance. Then the deposited energy could be found by integration of difference of powers. The capacitive probe provides the best resolution since it allows to resolve the propagation of the fast ionization wave in the capillary. And we can see that the measurements by the backcurrent shunts and the capacitive probe are in agreement after 30 nanoseconds. This is caused by the fact that the fast ionization wave reaches the low voltage electrodes and the electric current starts to flow. That's why the measurements of BCS and capacitive probe are in agreement. So far we have discussed how we are going to measure the electric fields and specific deposited energy. We are now ready to talk about the electron density, and we are going to talk about the spatial profile. It was done by the ICCD imaging. This is an example of ICCD image of the discharge. Then, as soon as the ICCD image of the discharge has been taken, the transversal probe of the discharge could be taken as well. Then, this transversal probe was built with respect to the radius, and then this is the black curve on the right-hand side of the screen. It is important to estimate the wall emission in order to subtract it, in order to understand the signal which comes purely from the discharge. And then we obtain the blue curve, which is the corrected profile. Finally, it is possible to apply the inverse Abel transform to the corrected profile and to have the distribution of N to C, which is in its turn related to the electron density. As for the temperature measurements, they were again done in a mixture of N2 CO2, and it is important to verify whether the fraction of N2 in CO2 mixture doesn't significantly influence the rotational temperature of N to C. And it can be seen that the normalized factor of the second positive system of N2 are in agreement at different fractions of N2, from 9% to 33%. Therefore, it can be concluded that the temperature of N to C shouldn't be dependent on the fraction of N2. Then, as soon as the normalized factor of the second positive system are obtained, it is possible to apply the spec air fit of the rotational temperature and to have the parameter, the gas temperature. So far we have discussed the most part of the experimental techniques, the experimental setups, and so on. And now we're going to talk about the experimental results. I'm going to present you the electrical characteristics, the temperature, the optical emission spectrum, and so on. As for the electrical characteristics, again, I will remind that there is a propagation of the fast ionization wave in the capillary, and the amplitude of the electric field in the front of the fast ionization wave is as high as 1200 Townsend. The average value of the reduced electric field after the front of the fast ionization wave is around 200 Townsend. The peak electric current corresponding to the electric field is around 130 amperes. The specific deposited energy in the first pulse corresponding to this situation is around 1 electron volt per particle, which is relatively high. The measurement of the specific deposited energy has been done also for various pressures, and they were both done in the thin capillary and the FTIR capillary. And in fact, it can be seen that the values of specific deposited energy at optimal pressures in the FTIR capillary and the thin capillary, the difference is almost 3 times. And this is caused by the fact that the low voltage electrode of the FTIR capillary was grounded. We have discussed the amount of specific deposited energy and the reduced electric fields, and we have seen that they are quite high. Now I'm going to talk about the measurements of the electron density. The temporal profile of the electron density was measured by a very interesting means. And this way to measure the electron density was based on the fact that there was a transmitted pulse coming from the discharge tube. Then, when this transmitted pulse came to the low voltage end of the low voltage cable, it would reflect from it. And then this pulse propagated back to the discharge tube. In fact, this pulse could act as a probing pulse and generate another triad of pulses registered by the BCS2 and BCS1. Therefore, it is possible to find the reduced electric field and the electric current, and then to deduce the electron density. And what is the most important, that it was possible to chop the cables and to vary the time of arrival of this probing pulse to the discharge tube. That's how the electron density was registered at different time instants. It can be seen that the electron density in the first pulse is as high as 2 times 10 to 15 centimeters minus 3, which corresponds to the ionization degree of almost 1%. We have discussed the temporal profile of the electron density, and it is necessary to describe the radial profile of the electron density, which is related to the N to C emission. First of all, it has been done again at different time instants, at different pulses. And the behavior of the radial profile of that electron density is in agreement for all the time instants. Moreover, if we build the normalized profiles, we can conclude that the electron density monotonously decays towards the radius, towards the walls, and therefore it can be concluded that the discharge kinetics is defined by the processes occurring at the axis of the discharge tube, or not on the wall, or nor somewhere in between. Alright, we have discussed that the electron density, electric field, and the specific deposited energy is quite high. And the optical emission spectroscopy will help us to understand which species are abundant during each pulse at these high values of the parameters. We will understand whether the dissociation of carbon dioxide occurs during the discharge, during the pulses, and we will understand how exactly big are our values of deposited energy and the energy of electrons. The optical emission spectroscopy was done both in the thin capillary and the FTIR capillary. As for the first pulse, it is mainly characterized by the presence of CO2 plus ions. the electronically excited states of CO2 plus ions, which are represented by the Fox-Duffendackett-Barker system and the ultraviolet doublet system. Then, the dissociation of CO2 is witnessed by the fact that there is a presence of atomic oxygen lines. And moreover, we dissociate CO since we have the presence of the carbon lines. As for the second pulse, it is qualitatively the same, but there is a very important difference. It is the appearance of the Swan band, which corresponds to the formation of the diatomic carbon. As for the third pulse, since its energy is the least energy among all the energy of the pulses, the relative intensity of the optical emission spectra are the least one. And we have the appearance of the third positive system of CO. I've done the same measurements in the FTIR capillary, and they have revealed that despite the fact that the specific deposited energy in the FTIR capillary is almost 3 times higher than in the thin capillary, there is no any qualitative difference. Now, it is important to understand how big is our deposited energy. And a good way to do so is to build the excitation threshold of the species which were observed in the experiment with respect to the ground state of CO2. In the first pulse, we can see that there is an ultraviolet doublet system and the FTB system, and the excitation threshold is as high as almost 20%. Then we have the atomic line, which corresponds to the dissociation of CO and excitation of carbon, and it means that there is a significant amount of electrons whose energy is more than 20 electron volts. And moreover, we not only dissociate CO, we excite it. It can be witnessed by the presence of the fourth positive system. The dissociation, the threshold of formation and excitation of diatomic carbon with respect to CO2 is equal to 25 electron volts. And as for the third pulse, the energy of the pulse is less than in the previous first and the second pulse, and we have the presence of the third positive system. It is important, it is interesting that it was quite conventional to observe the angstrom band instead of Swan band in the discharge spectrum. And the fact that we didn't observe the angstrom band in the capillary and observe the Swan band was interesting. And there were 2 experiments which was focused on the angstrom band, on its presence. The first experiment is the following. We made a PMT measurement of the intensity, of the temporal profile of the intensity of the emission of the discharge at 515 nanometers. And it can be seen then it is the Swan band since it exactly appears in the second pulse and not before. Another experiment which was dedicated to the angstrom band in its presence was the measurements at relatively high pressures. The increase of pressure was dedicated to the decrease of the specific deposited energy and decrease of the reduced electric field. And it can be seen that the angstrom band starts to appear as the pressure and the specific deposit pressure is increased on 2 times and the specific deposited energy is decreased on 2 times as well. In conclusion, we can see that there is a significant part of the electrons whose energy is around 20 electron volts. And it is interesting to understand how it influences the gas temperature. The measurement of the gas temperature were both done in the FTIR capillary and the thin capillary. Of course, the amount of the specific deposited energy in the FTIR capillary is almost 3 times higher than in the thin capillary, and it can be seen on the difference of the temperature. Nevertheless, the effect of the fast gas heating is pronounced for both of the capillaries, since even for the thin capillary, the increase of the temperature at sub-microsecond timescale is more than 1000 kelvins. Therefore, the phenomenon of the fast gas heating in the capillary discharge can be confirmed. So far I have discussed the most part of the experimental results, and now it is necessary to explain them by zero-D numerical modeling. The zero-D numerical modeling was done by the so-called code ZD+K. First of all, it used the temporal profile of the electric field measured by the capacitive probe as the input data. And it has several peculiarities, and I will explain how to circumvent them. First of all, the initial electron density was an additional input parameter, and it was chosen in such a way that the experimental currents in the first pulse are in agreement. The experimental and modeling currents are in agreement. Second, it is essential to remember that the zero-D+K code is based on the solution of the Boltzmann equation, and it solves the Boltzmann equation at different time instants. Therefore, it means that if the electric field between the first and the second pulse, or for example between the second and the third pulse, is equal to 0, the electron temperature will instantaneously cool down to 300 kelvins, which of course is not physical at all. A way to circumvent this problem was the following. In fact, there was a fictional non-zero electric field which was introduced between the pulses in such a way that module and experimental currents in the second and the third pulses are in agreement. Finally, it is important to remember that we still deal with the zero-D code, and therefore we couldn't take into account any spatial behavior of the discharge. For instance, we couldn't take into account the movement of the electrons toward the walls, and therefore we used an additional term which was responsible for the decay of the electron density on the axis. And this term was introduced in order to make slight corrections of the agreement of the experimental and model currents. We're now ready to talk about the processes which were used in the experiment. The processes could be divided onto three main groups. First of all, the first group, this is the electronic interaction with the CO2 and CO molecules. It included the formation of the CO2 plus ion, dissociation of CO2 molecule by electron impact, and excitation of CO. The second group is the biggest one, and it includes the quenching of electronically excited states of CoA and O1s and O1d formed in the first pulse, and this leads to the gas heating. The gas heating could be taken into account by the energy defect for each reaction. It is important that the calculations of the gas temperature were done according to the temperature dependence of the specific heat of the mixture. The third part of the reactions are the reactions over interaction of over ions and electrons, or ions and the neutral particles. So far, we have discussed that the electronic degrees of freedom of CO, O1s, O1d are the species which are the most dominant for the behavior of the discharge at sub-microsecond timescale. However, to be even more precise, it is essential to apply the vibrational kinetics and to study its role. To do so, 21 levels of the asymmetric modes of CO2 were included. And it included the VT exchange, which is in fact the transfer of the vibrational degrees of freedom to translational degrees of freedom, or in other words, the gas heating. And as for the VV exchange, which is in fact is an exchange of quanta, or vibrational quanta between two vibrationally excited molecules, it was also taken into account. It is important that the VV exchange is the process which is responsible for the formation and for the establishment of the vibrational distribution function. Their calculations are presented in the slide, and they have been done for the different time instants. It can be seen that the vibrational distribution function starts to be populated at the first nanoseconds of the discharge. Then it can be seen that it is highly populated in the end of the afterglow of the first pulse, and during the second pulse in its afterglow it is almost constant. It starts to decay only at the time instant of around 500 nanoseconds. It continues to decay at the time instant of 1 microsecond, and it is almost completely decayed on 2 microseconds. Therefore, it can be concluded that the VT relaxation shouldn't contribute so much in the gas heating at sub-microsecond time scale. To confirm this, we did the temperature measurements, temperature calculations of the by the 0D plus King code. They were both done for the case with vibrations and without vibrations. It can be seen that the both curves are in agreement with the experimental data, are in a good agreement with the experimental data at sub-microsecond time scale, and the role of vibrations is negligible at before the time instant of 600 kelvins, about 600 nanoseconds. However, it is important to take the vibrations into account since they provide an additional effect of the gas heating on almost 1000 kelvins after the time instant of 600 nanoseconds. Another evidence of the validity of the kinetic scheme is the comparison of the electron density and the calculations of the electron density and its measurements. Indeed, the electron density measured and the calculated are in good agreement. It can be seen as well that the electron density is counterbalanced by the CO2 plus and O2 plus ions. Finally, it is important to understand which processes are the most essential ones. On the left-hand side of the screen, we can see the reaction rates with respect to the time in all three pulses. First of all, this is the quenching of O1D to O3P, which makes the additional excitation of vibrational levels of CO2. The rest of the energy defect comes to the translational degrees of freedom. Then the COA is quenched by atomic oxygen, and then atomic oxygen is excited to the O1S. In fact, the O1S fissure acts as a reservoir of the additional energy, which is responsible for the additional gas heating and the additional dissociation during all the three pulses. It can be seen that O1S, in fact, this is the most essential species, and it is, since it's the most abundant excited species during overall the pulses. Finally, it can be seen that the dissociation fraction at a single triad of pulse at microsecond time scale is equal to almost 16%. And now it is interesting to understand how much CO2 will have in the end, in the steady state. To answer this question, we applied the FTIR measurement of the CO2 dissociation fraction and the energy efficiency. The measurements were done at different pressures. The dissociation fraction and the energy efficiency would be defined according to the following formula. The figure next to an experimental point designates the number of pulses treating the portion of gas. It can be seen that the 8 millibars is the optimal pressure for the dissociation fraction and energy efficiency. And moreover, it is possible to enhance the dissociation fraction by the application of high voltage, high frequency pulse regime. In fact, it is possible to reach the saturation threshold of the dissociation fraction of almost 90%. The energy efficiency corresponding to this is as high as almost 10%, which is quite good. The measurements of the dissociation fraction with respect to the applied peak voltage shows the fact that there is a threshold of the applied peak voltage. It can be explained by the fact that the electron has to have a certain amount of energy in order to destroy a CO2 molecule. I'm now very close to the conclusion part of the presentation. First of all, it is important that the nanosecond capillary discharge was very stable and was developing in the form of the fast ionization wave. It was reproducible at the pressure values of 10, 20 millibars. In other words, at moderate pressures. And the optical emission spectroscopy has revealed the fact that CO2 dissociation by electron impact is the dominant mechanism in the discharge itself. In other words, it's sub-microsecond timescale. And then, the specific deposited energy and the reduced electric fields are so high that they facilitate the gas heating on almost 1 to 2000 kelvins at sub-microsecond timescale. The processes which are responsible for this are COA and O1S, O1D produced in the high voltage pulses. The 0D numerical modeling, which included both formation of the electronically excited states and included the formation of the vibrational manifold, has revealed the fact that the VT relaxation becomes important only at microsecond time scale. And finally, the steady-state measurements of the dissociation fraction in a single pulse has revealed the fact that the energy efficiency and the dissociation fraction are about 20% at 8 millibars. And it is possible to increase the dissociation fraction up to 90% at multi-pulse regime. The final words, the final acknowledgements comes to the RNR Aspen project and Lea Kappa project. I appreciate your attention and I'm looking forward to the questions. Thank you.
Okay. Thank you, Georgy, for staying well within the time allotted. I don't know if there will be the standard exodus of people from the amphitheater who have other engagements. Is everyone sticking around for questions, or are people filing out noisily? It sounds quite quiet there, so I think we can just start away with questions right away.
Sure.
Good. Okay, so I propose we begin with the two rapporteurs and starting with Vasco Guerra, who is ready. Yes, good. Okay. So please turn on your microphone.
Yes, thank you. Good morning to everybody. So just before I start, so more or less how long do I have? How much time do I have?
There's no official time limit, so please feel free to ask the questions that you feel have to be necessary to be answered.
Okay, so good morning everybody again. So first I'd like, of course, to thank the supervisor, Dr. Svetlana Pokrovskiy, for the invitation to be part of this jury and to Ecole Polytechnic in general, in this case the person of the president of the jury. So it's a pleasure to collaborate in this type of events. And of course, a special greeting to the candidate, Georgy Pokrovskiy. I wish you all the best, of course, for this day. It's your day, so enjoy it. So first general comment is that this is a work that involves a significant experimental component and a significant modeling component, which is something that I always like to see. So, congratulations, it's very nice to see people trying to develop competence in both these topics. I made on my report also minor remarks on the form of the manuscript. So these are, of course, suggestions. Form is a question of taste. So I will not go on those, they are written, so it's fine. So my first question, it's more this context question, more speculative on the view on how to look at the problem, is related to this picture that you have also shown in the presentation, that everybody more or less reproduces in the paper dealing with CO2, with these potential curves and so on. So I try to play a little bit devil's advocate here, and you know that you could turn the questions on me as well, because I follow the same things. But what I want to point out is this is, of course, a projection of a 3D potential energy surface. And so, in fact, the molecule has to bend in order to pass from one state to the other. So the crossings are not where we look at them in this picture. So this can be a bit misleading. And these questions first, if this ladder climbing along the asymmetric stretching mode is something that we should really consider seriously, or is this really a very naive vision of the molecule? Also, you see there the last vibration level that you represent in this figure is already on the curve of the electronic state. So, of course, if we just consider asymmetric modes, it should be on the curve of the ground state, so it should be on the curve to the left, not there. So there is a transition to an electronic state also. So when we do all these VV and VT calculations, we are forgetting for important details on the configuration of the molecule. So this is my more speculative question. How do you see this happening, and the interest and validity of using this approach on the ladder climbing along the asymmetric stretch level, taking into account this more complex context of the real molecule with 3 atoms?
Okay, thank you for the question. Okay. Okay, well, we know very well that the CO2 molecule is a triatomic molecule, and indeed we have to take into account not the potential curves, but the potential surfaces. But well, this is, in fact, this is one of the simplest way to describe the vibrational manifold, these 21 levels of the stretching mode. And the previous researchers has revealed the fact that they provide the good agreement with the experiments, and still it is a very powerful instrument. And if we take into account the vibrational levels which are situated on the surfaces, well, in fact, they can't be considered as constant energy levels, and they probably have their how to say, some dependence on the spatial coordinate, and I think it is quite complicated to take it into account.
Yes, thank you. Yeah, I know this is a difficult question. We all need to start somewhere. We all need to start somewhere. It's more a question of thinking, more how to move forward. So if I make a blunt statement like, in the end, maybe the details of these state-to-state exchanges are not so relevant. As long as we get the general input of energy right, and the initial upflux of vibration energy up the ladder, it doesn't really matter what we consider, because we will arrive at more or less good results. Would this be something that you
Okay, so if I can precise your question, do you imply the fact that the constants of the VV exchange are overestimated?
Okay, I was going to that point later. It's not really what I mean. What I mean here. What I mean is this is again speculative. I'm not. I'm really discussing for the pleasure of discussion and trying to put it as ideas for future developments of this type of models. So the question is more. Okay, the previous question was an attempt to show that okay, we are making an oversimplified view of the model, and you answer okay very accurately that it is true, but if you use this model, we get a good agreement with experiment in many other discharges that have been tested. So maybe in the end, that's my question, maybe in the end, these details of the state-to-state are not so important. So considering 21 levels or considering other exchanges to electronic states, when we approach the very high energies, maybe the results of the model are not so dependent on these assumptions. If we get right the input of vibration energy and the flux of energy from the bottom of the ladder to the top of the ladder a little bit, if this is more or less correct, then maybe, this is the question, maybe it's not so important if we have 21 levels, if we cross to other electronic state or not, at least on the zero order. So this is, but the question is, would this picture a bit more rough and more broad, something that you would think it is worth exploring, or you would go on the other direction maybe to try to complicate more and put in very big detail the transition to electronic states and so on.
Okay, thank you, Vashka, about the question. Well, we are working in nanosecond discharges, and let me move probably to the slide. To the slide where I'm showing the difference of the temperature, which is calculated with vibrations and without vibrations. Of course,
we can't see the.
you can't. Sorry.
But for me, it's fine. I have it. I know which slide it is.
Okay.
It's okay.
Okay, we can see that the temperature difference before 600 nanoseconds with and without vibrations is not significant. Second, the dissociation of CO2, which is due to the vibrational manifold, is less than 10%. And as soon as we know that, in fact, that the rate constants are overestimated, and the vibrational kinetics, well, it is important to learn it probably, to study it at microsecond time scale. And in order, for example, to study the VT relaxation, the recombination, and so on. But in fact, it can be seen that it doesn't play a very significant role at sub-microsecond time scale. So probably if we are talking about the discharge kinetics at sub-microsecond time scale, I wouldn't make this model very complicated.
Yes, okay, so this enters a question that I got for later on, but I can put it already here, which is if you have in mind, in fact, which vibration levels are contributing more to this gas heating that we see here, if that is possible to separate. Like, is it more up to V10 or V5, or is the levels like around 18? I don't know. If you have an idea of the actual V levels that are contributing to this gas heating that we see here.
Okay, thank you. It can be seen that Do you see the cursor?
Here.
Sorry, yes.
Okay. It's forward.
No.
It can be seen that the VT relaxation starts at a time instant of approximately 500 nanoseconds, and it starts with the level, probably the level 15 and higher. Yeah.
Okay. And also the similar question regarding the dissociation. So you said that there is vibration dissociation or dissociation from vibration excited levels. It contributes less than 10% to the total dissociation.
Yes.
I don't know also if it is possible, or if you have the information of if there are some specific levels that are dominant on this 10%, or if it is distributed along the VDF.
Okay, so unfortunately, well, I didn't take a precise look on the role of of each particular vibrational levels on CO2 dissociation, but well, I can suggest that again the higher vibrational levels are responsible for it. Yeah, they're higher than 15, I guess.
Okay, then I think that would be useful information. You have everything in the model, so it's not so difficult to check. It would be interesting to know. And also if it is through this pure vibrational mechanism or by electric impact, because you consider all the transitions by electric impact along the V levels, so that's also easy to check. Okay, so I had another, I will skip many of the questions that I have in the report, otherwise I could stay here long time. So I will ask now regarding an assertion that you made in the thesis that it was on chapter 4 that the results would be representing dissociation in a single pulse regime. Also, some sentences like the most significant level of dissociation occurs in the first pulse. So maybe I missed the point, because looking at the dissociation pictures and also this scaling with number of pulses, I had the impression that this was not really the case. So I don't know if you can clarify a bit these statements.
Okay, do you mean the sentence that the dissociation occurs in the first pulse?
Yes.
Okay, it is related to the fact that we see the optical emission spectrum in the first pulse, and we see the atomic oxygen and atomic carbon lines. Therefore, it can be concluded that the dissociation occurs in the first pulse. Then, it can be seen that the dissociation fraction with respect to the pulse repetition rate is has the linear dependence. Therefore, it can be concluded that it is proportional to the number of pulses treating the gas portion.
So I think it was my misunderstanding on the phrasing, because I think we are saying the same thing. Just I was putting a different meaning on the words. So the other issue that interested me quite a lot was this time evolution of the electron energy distribution function. That is not considered here because you are using CD plus skin and Boltzmann simulation tools. You use what I call this quasi-stationary approach, like the EVF response instantaneously to the value of E over N, which I think it's maybe not true in this case. So this is the first question. And related to having doubts and questioning how precise or how good is this estimation of the electric density for a star. So I don't know if you can also elaborate a bit on this question.
Okay, thank you. There is a ratio which is designated by the theta letter, which describes the rate of the relaxation of the electron energy and the rate of the change of the electric field. This is the parameter which is in brackets, can be calculated easily from the experimental data. Then this parameter nu, which is the frequency of relaxation of the electron energy, can be calculated by the following formula, where VE is the electron mean energy and the lambda is the mean free path of electrons. Then we can conclude that even in the fast ionization wave, this parameter is approximately equal to 40-60 in our conditions. So it means that the time increase of the fast ionization wave, the characteristic change time of the reduced electric fields is lower than the frequency of relaxation of energy. Another point is that the fact that we controlled the probing pulse. When we were measuring the temporal profile of the electron density, we used the probing pulse. In fact, it had to be sufficiently low in order to not to make any additional plasma. We controlled it by additional resistance which was soldered on the low voltage cable, and we controlled the fact that we didn't have any increase of the electron density on the time instant of interest, and so we had to have a plateau instead of something like this. And since we had a plateau and we have this relation, we could be more or less okay with the measurements of the temporal profile of the electron density.
Yes, I understand those estimations, of course. So it's still it's always something that disturbs me a little bit. I think it's your expression in the end. It was we are more or less okay. I think so. What is more or less that we are trying to evaluate here. But I will not continue on this point because I think it's more or less fine. So it's a point that I think it's a bit dangerous. It's not. I don't say that. Maybe it's completely right. Maybe it's completely perfect. But it's a bit on the edge. That's also something to pay attention to. So this same approximation. Sorry, another question on this point that I forgot. Do you consider the changes in the mixture on this estimation? Because CO2 is being dissociated, and so you start getting a mixture of CO2, CO, and oxygen atoms at least, and of course then mobility is changing and so on. So I don't know just if you are using always the values taken from pure CO2, or if you are considering the update of the mixture as you do this calculation.
Yeah, okay, so it was always pure CO2.
So the other related question to this quasi-stationary approach is this zero over n between pulses. So this is an interesting way to avoid the difficult.
Mm-hmm. He stopped his microphone.
Last I think you muted your, yeah.
Sorry. Yes. So the question is first if you can give us an idea of the value of this over n that again, this relaxation of the energy to estimate the time-dependent evolution of the rate coefficients, but maybe that is unnecessarily complicated.
Okay. So as for the reduced radiative fields between the pulses, it was around 20,000. Well, it was a constant plateau of 20,000. Then it was checked by the comparison of the electron temperature, which was again calculated by the ZD+Kim, and the vibrational temperature. Well, in order to confirm the physical point, the temperature should have been more or less in agreement. And they were equal to approximately 5,000 kelvins.
Okay. And looks like a reasonable value to me. Also, you have here in this slide that you add the diffusion of electrons to correct a bit for the, I guess, the comparison of electron density with experiment. So first, I had the impression that this was the free diffusion coefficient that you use
Yes.
for electron. And it relates also to the graph on the evolution of charged particles. You have electron density and positive ions. And then at a certain point, of course, you don't have a quasi-neutrality in your plasma, if I look it correctly. I guess because you are not considering the diffusion of the ions, probably. So the question is related to this. So which value of the diffusion should we take for the electron losses? And if this is a problem that in the end you are not keeping quasi-neutrality in your simulations on this.
Okay, yeah, thank you for the question. In fact, these are the 0D calculations. Then it means that we have calculated the electron density, the gas temperature, and the rest of the parameters on the axis of the discharge. And of course, well, I only took into account the diffusion of electrons. The characteristic sign of the diffusion of electrons in our scheme is around, I would say, hundreds of nanoseconds. And this is the free diffusion, because the ambipolar diffusion takes a significant more time, about 10 to minus 4 seconds. Then it was not possible to take into account the diffusion of ions. And for example, it is possible to take into account the spatial coordinate of the discharge tube, and it can be seen that it could be seen that there is a different behavior of different ions with respect to the radius of the tube.
Okay, so I think I understood it now. So you are representing or using the 0D model to represent the axis of the discharge,
Exactly.
not the average, the volume average of the species concentration.
Yes.
Okay. Because if okay, 0Ds can also be seen or built in a way as to represent the average, the special average properties of the discharge. And in that case, you can include diffusion for all species and so on, but it has a different meaning and a different interpretation than what you are showing here. So, okay, so I understood it now. Of course, if it is average, quasi-neutrality should hold, but not in the axis, maybe not necessarily so. Okay, still. Yeah, but I see that it's a very local issue. Okay. So I was curious to see or to know. You mentioned that you used some sensitivity analysis to reduce the number of reactions and species. So this is
So we did the sensitivity analysis with respect to the CO concentration on time, and in the very beginning there were around 170 particles. The main particles which were discarded are the negative ions, O minus, O2 minus, O3 minus, and so on. And in total, we had about 100 reactions, which didn't take into account their negative ions. And there are 21 main reactions.
Okay, good. Yeah, it was really curiosity, but it's interesting to know, in fact. Okay, thanks. Yeah, if I'm allowed, I will still continue just for my maybe 5-10 minutes more. Okay. Yeah, I wanted to enter a topic that we already addressed a little bit regarding this the details of the calculation of the VDF, because as I noted, I have this feeling, maybe wrong, but I have this feeling that they are a bit overpopulated, in fact, and that this came from both EV rate coefficients used and the VV rate coefficients used. So of course it's quite an unfair question, because I say I have the feeling that, but you work with this many years, so you have probably your own feeling. So let me start then with the electrons. So first with the electrons, it's this question of all the stepwise excitation mechanisms. Okay, so there is this technicality on what is the Friedmann approximation. So I don't want to, this is not an issue. I mean, we use many different variants. My view is that the real Friedmann approximation does not have the threshold shift. I even wrote in one of my papers the same as you, and then I realized that it was probably not, or it was not the way to go, but that's not what I want to say. It's not to discuss the name of the approximation, is more this really feeling that I have that this approximation provides too high EV rate coefficients. It also relates to this question of using stepwise mechanisms up to V22. How realistic is this? And if we should not consider electron impact dissociation from vibration excited levels through the electronic states as we consider from V equals 0. So I made many questions in one. Let's divide, so let's look at EV mechanisms. And so a comment on the different ways to estimate these stepwise excitation processes. If you feel or not, like me, that this gives too high EV rate coefficients, and how to account for dissociation effect from vibrationally excited states. If we should consider also the transitions to the electronic states, or if we should focus on the stepwise V21 to V22.
Okay. All right. So indeed, yeah, this approximation of, for example, of VV exchange and the EV constants are overestimated. It means that we overestimate the role of the vibrational kinetics. And as soon as I said that the dissociation of CO2 by vibrational degrees of freedom contribute less than 10%, so it's in fact that if we apply the real constants, the real parameters, the real role of vibrations will be even less. However, it is true that since we were discussing in your first question that a CO2 molecule has that doesn't have any energy levels, but it has more energy surfaces. Well, we have to take into account the dependence on energy with respect to the spatial coordinate. Well, this would be complicated. I think that a good way to enhance the model would be the introduction of the Arrhenius term. It means that the dependence of the rate constant on the temperature, for example, on the electron or vibrational temperature. And this wasn't taken into account here.
Okay. Okay. Yeah. So the other we discussed just a bit this EV. So the VV you already mentioned before. So they are also they are clearly overestimated. So we go above gas kinetic rate with these expressions. It's of course too much. It's maybe not too critical because we have direct and reverse mechanisms, and the time constants are relatively low for what you are evaluating. So it's maybe not, but it's true that they are. Okay, so I think I will just make one last question. The others on my report. Okay, feel free to adapt the thesis if you find any of them relevant. And if there is something that you strongly disagree, we can then discuss in another context. So the final question is just if you have any comparison of or conditions of the simulations that you could compare with the actual dissociation that you measure. Because I think I didn't see that figure.
Okay, yeah, this is a very important question. So far, we have to take it, well, it wasn't done yet because we had to take into account the thermal dissociation of CO2, the recombination on walls, well, and some other ways of recombination of CO2 in order to, let's say, to extend the calculations from the microsecond time scale to the milli and, well, to the second time scale. And of course, it will be interesting to do this, but well, it's not can be done yet. So far we have really done the model which works quite well on the sub-microsecond time scale. But of course, yeah, the development of this problem is essential.
Okay, so I think it's also related a bit to what is the zero D that you are doing, that you need then the walls and all these.
Yes, exactly. Yeah.
Okay. So sorry, I promised it was the last question, but a very big last question now. So related to this fast gas heating, I understand that okay, you still want to prepare the publication with all this data and so on. But you mentioned that you have COA, O1S, and O1D that are relevant for the fast gas heating, and we see their densities that are important. So without entering in any details, the question is there a winner among these states that contributes the most to the gas heating, or are they contributing more or less equally, or depending on the time that we are looking at, they will contribute in a significant way?
So it should be O1S, which is the winner, and it is interesting that it is formed by the fast quenching of the COA ions to O1S. And yes, then it acts as the species over the biggest importance, let's say.
Okay, thank you very much. So I'm here with thank you again.
Thank you.
Okay. Very good. Thank you very much. And so the next person to ask questions will be Nicolas Georgy, second rapporteur.
Good morning, everyone. I would like first to thank Svetlana for this invitation, and congratulations for your nice presentation and your manuscript. I have lost a lot of questions during the last 30 minutes, but my first question is about the experimental setup. During this work, you used two different discharge cells. In both cases, it is a capillary discharge, but the internal diameter and the materials are different. Can you comment this effect on the discharge and also on the CO2 conversion?
Okay. So the main difference of the capillaries was their construction, was not the construction but the configuration. The fact that the specific deposited energy and the FTIR capillary was almost 3 times higher due to this grounding of the low voltage electrodes. Then,
Georgy, could I ask you the one time we can't see the slide, I think.
You can't see the slides?
No, we still see the relaxation.
Sorry, okay.
I'm interested in this part. So.
Okay.
Yeah, perfect.
Okay. So, and the difference of the radii between the capillaries wasn't really significant, just close to the difference of this grounding. Then the capillaries were fabricated from different materials. The thin capillary was fabricated from quartz, and the FTIR capillary was made from glass. But we didn't observe any significant difference on the species since we have done the optical emission spectroscopy in both capillaries, and we didn't reveal any qualitative difference. But what was important that the spectroscopy, optical emission spectroscopy, was simpler in the thin capillary because it was made from quartz, which is transparent for the wavelength below 300 nanometers. And for the FTIR capillary, for example, we couldn't observe the fourth positive system of zero because it wasn't visible.
Okay, but the gas temperature is quite different in both cases.
Yes.
So, what is the impact on the CO2 conversion?
Okay. Okay, I'll answer like this. The gas temperature in the FTIR capillary is higher. Then, so we can see that the plasma, sorry, not even the gas kinetics after the discharge in the afterglow should be different. And so far we've done the measurements of the steady state values of the dissociation fraction only in the FTIR capillary. It will be then important to measure to make the Talif measurements in the thin capillary in order to understand how many CO2 we have in the discharge, and probably to have the measurements by the FTIR in order to compare. So far we have like a little bit. So we have a thin capillary and the FTIR capillary. We have an idea what happens at sub-microsecond time scale in the thin capillary, and we have an idea what happens at millisecond time scale in the FTIR capillary. And I think that in the thin capillary the dissociation factor should be less, since the specific deposited energy is less. And
but the gas temperature is lower also.
Yeah, and the gas temperature is lower.
It is better.
But we have the VT relaxation.
Yeah.
And also it is thinner. It's thinner, so probably we'll have a faster recombination of CO and O on the walls.
So in the future it will be maybe easier to use the same tube in both cases.
Yes, I think so.
Characterize the discharge and the
It's not even well. It's not even question. Well, it's not question of the diameter. It's really, I think, it's question of the configuration.
Yeah.
Yeah.
If I continue on the gas temperature, in your manuscript there is a lot of discussion about the gas temperature, and there is evidence of significant gas heating. However, you always consider a temperature equal to 300 Kelvin.
Yes.
Can you comment the effect of this higher gas temperature on your calculation in your manuscript, and what will be the effect, for example, if I come back to the manuscript. For example, in chapter 4, you always consider 300 Kelvin for all your calculation, and what will be the effect, in fact? At the end of your manuscript, you say, okay, the gas temperature is not 300 Kelvin, but it can be up to 1000 to 2000 Kelvin.
Mm-hmm.
Okay.
Yes.
But there is no comeback on the previous part, in fact. So it's quite difficult to understand for me this effect on the previous chapters, in fact. Okay, so now you know that the gas temperature is higher. Okay, and so what?
Mm-hmm. Okay, so we have discussed, and well, it's mentioned in the manuscript that that it's not exactly the temperature which matters for the calculations of the number of pulses treating the gas portion, but more the gas density.
Yeah.
And if we make an estimation, it can be seen that the gas density, let's say that it doesn't have enough time to respond to the increase of the temperature. So the temperature is increased, and then the gas is already cooled down by the heat transfer to the walls, and only after the gas density will, let's say, feel the increase of the temperature. So that's why it was always considered to be frequent. Yeah.
Can you come back to the slide 25?
25.
Sure. With rotational temperature.
Rotational temperature. Yes.
Yeah, this one.
Mm-hmm.
You had a huge quantity of nitrogen in your CO2 discharge, and it's quite difficult for me to view here that there is no effect of this nitrogen on the discharge, because the quantity of nitrogen is always very high, in fact, for me. Did you try, for example, to add only few ppm of nitrogen to check this effect on the discharge?
So the least amount of nitrogen we inserted was 2%. Yeah. Still,
and it's really high, in fact, 2%. It can change a lot of things.
Yes, that's true. The problem was that, we had the experimental limitations, which was connected to the, let's say, to the error of the flow controller.
Yeah.
And for example, if we decreased less than a certain point, we couldn't be sure whether we have an exact amount of flow or not.
Okay, so it's difficult to
Yes.
inject.
So it's really, of course, it's an innovative measurement.
Yeah. Okay. During this work, you work only at reduced pressure between, I think, 5 and 40 millibar.
Between 5 and between 5 and 20, between 5 and 30, yes.
Did you try to increase more the pressure?
Yes, we tried. The discharge stops to be ignited at approximately 50 millibars. So it's, well, we couldn't observe the propagation of the ionization wave, and, well, there is simply no current.
Okay.
Yeah.
So, in your opinion, what will be the effect of higher pressure? I mean, few hundred millibar up to atmospheric pressure.
Okay, so if we are talking about the capillary discharge, if we increase the pressure up to 100, even higher, well, we will lose this this clue of a high amount of specific deposited energy, and therefore well, we have less ionization, we will have less electron density, and of course we will lose everything.
Okay. So only at low pressure.
Huh?
So this discharge is interesting in this configuration only at reduced pressure. So you think it is not possible to obtain a high dissociation fraction at higher pressure in this configuration?
High dissociation fraction at high pressure.
Yeah.
Yes. So yeah, we'll just go like this. Just a second, I will scroll to the slide, and I will continue the screen sharing. Okay. So yeah, we have the decrease of the pressure, decrease of the dissociation fraction at high pressures. Again, this is caused by the fact of the decrease of the specific deposited energy.
Okay. Can you compare your results with the state of art of CO2 conversion using cold plasma? I mean, a brief comparison between DVD discharges, the microwave, gliding arc, and so on.
Mm-hmm. Okay. Just a second. So, I would say that, for example, at high repetition rates, we can see the dissociation fraction of almost 90%. So we have, in fact, we had the increase of temperature. So I would say that it probably resembles a little bit the microwave discharge, since we have the high repetition rate and the gas heating. The difference among this discharge and the microwave discharge is the low energy efficiency. But instead we have the high dissociation fraction, which is apparently due to the electronically excited states. And as for the energy efficiency and dissociation fraction in low frequency pulse regime, it can probably can be related to the glow discharge. But the problem of the capillary discharge is that, despite the fact that the fraction and the efficiency are relatively high, there is a very important problem. This is the capillary discharge, and it is very small. So it is well, it will take a long time to produce a significant amount of CO in oxygen for some reasonable quantities. Okay.
Maybe one last question. If you could change one thing about your work or your scientific approach during this thesis, what would it be?
So first of all, of course, I would probably make the numerical modeling for the millisecond time scale, because, well, it's really interesting what happens after. And it's really interesting how this data on the FTIR capillary was related to the numerical modeling and so on. Then I would probably do the measurements of the same measurements of the dissociation fraction at different capillaries. For example, in the longer capillaries with the same diameter and in the wider capillaries with the same length, in order to understand the role of the electric fields and specific deposited energy. We even have these capillaries, but unfortunately, well, we didn't have time to make the experiments. But fortunately, well, one day the experiments will be done.
Okay. Thank you.
Thank you.
Congratulations again. Really interesting.
Thank you.
Thank you. And that worked quite well, because at least I could hear the question quite well. Thank you it's a good spot to stand for people listening. So the next person for questions, I think that we will go to Gianpiero Corona.
Yes, thank you. Okay, I have to say that Vasco asked most of the questions, so
Did a good job.
he left very few. But anyway, I really appreciate the thesis. It was written very well, and also the organization. Okay, Vasco is right that the chapters are too small, but this is just a question of taste. I think that the literature survey was quite good. The description of the experiments and also the theoretical basis of the experiments is very detailed and I really appreciate it. And also the description of the model is very nice. There were one comment, the first comment that is related to what has been asked before, is related to the stationarity of EF and on the dependence of EF on the composition, and not only on the composition but also on the level population, because you are considering a lot of electronically excited states. Maybe you can have strong effects due to superelastic collisions. Can you comment on this?
Okay, so if I correctly understand your question, what is the role of the EEDF on the superelastic collisions? And
the contrary. What is the effect of superelastic collision
on the EEDF?
And on the wall kinetic system?
Okay, well, okay, I have to think. Well, in fact, we form the electronically excited states. We form COA, we form O1D, O1S, and they mostly increase the gas temperature, and the answer is well, I can't really answer this question like from scratch. As well, I have to think about it.
I understand that this is something you are not experienced in, so I think that you can have just help you in this, because if you are giving back energy to electrons from electronically excited states, for example, you can mitigate the fast heating, for example, because you are giving back energy to electrons. This can be an effect. And moreover, you will not need, for example, the extra field in the interpulse plane. This can be important also, because usually when you have superelastic collisions, they can sustain the electrons, also when the electric field is not present. Another, let me look to my notes. That means that it is important also to use a self-consistent model, because in this short time of, it's not only a matter of the relaxation time, but also EDF relaxed together with the composition level distributions, and this can make some difference in the whole evolution of the system.
Okay, whether the change of the EDF will influence the whole evolution of the system.
Yes, sure.
Okay.
Because all the system is bound by the EDF. In your case, your model always consider everything is driven by the EDF.
Sure.
By the electrons. So everything can change if you include the distribution, including the rate coefficients.
Yes, sure. So as far as we have calculated the ratio of the, there is a parameter which describes the relaxation of the electron energy and the ratio of the rate of the relaxation of the energy of electrons and the rate of the change of the electric field. And
but in this formula, you are not considering superelastic collisions.
Well, still, this is we didn't consider the superelastic collisions. Of course, this is the mean free path is probably calculated in relatively low electric fields, but the change of the electric field was taken from the experimental data, and we can assume that the electron density, that the EDF has enough time to reply to the change of the electric field. But again, so these calculations, yes, they haven't been done with the superelastic collisions. Yes.
Mm-hmm. I know, because you were using pulse.
Exactly. Yeah.
I understand, but I just wanted to know if you can guess what's happening. But anyway, another problem also related to this is the use of the tail balance principle for recuperation. You make some consideration of this, but this consideration, I think, are valid only for low threshold transitions. I think this is under population above 10 eV for the distribution. So applying the Bell balance principle give another estimation of the reverse process, in my opinion. What do you think about it?
Okay, so are you talking about the population of the vibrational levels?
Yes.
Okay.
You were talking only about the vibrational levels?
Sorry, well, I was discussing the principle of the detailed balance for the correct description of the vibrational manifold. Yes, so I was, in fact, I was applying the principle of the detailed balance in order to calculate the rate constants of the the rate constants of the de-excitation of CO2 vibrational levels by electronic impact. And the Maxwell fit of the EEDF has shown that for even at low time instance, at units of nanoseconds, the behavior of the EEDF resembles the Maxwellian distribution function, and it means that for the electrons we can assume that there is an establishment of the detailed balance.
But that's tried good for vibration, not for electronically excited states.
Yeah. This is another point, and so far, I didn't take this into account. We have to.
You don't consider detailed balance for electronically excited states?
Sorry?
You did not consider the detailed balance for electronically excited states? For the reverse?
Well, the rate constants of the reverse reactions, of course, they were calculated according to the Arrhenius, to the Arrhenius equation. So, yeah, so it means that there was a direct balance, detailed balance for the most part of the reactions.
Just to go to another, so I will make just another question. Let me see. No, just a question. Why you are using an estimate of the diffusion? Pokrovskiy didn't calculate diffusion for electrons.
So Pokrovskiy calculates the ambipolar diffusion, but it also calculates the, it only calculates the diffusion coefficient.
For electrons, yeah.
For electrons, and ambipolar diffusion and simple diffusion, the free diffusion. But it only calculates the rate coefficients with respect to the electric field, and if we want to apply the decay rate, as an additional reaction, we have to implement it in the Z-Detla scheme.
Okay, thank you. Just another, I'm curious, in your model I didn't see carbon atoms in the kinetic model, while your measurements says that you have a lot of atoms. And at least the spectra, the signal of the atoms is very high. And also C2 is very important.
Okay. In fact, in the previous, let's say, in the first version of the 0D model, I was taking into account the carbon atoms, the carbon ions, the C2 and C2 plus ions, and eventually the sensitivity and even the rate analysis of the reactions which was involving these species has shown that these reactions are negligible. The point is that the optical emission spectroscopy is a very sensitive instrument, so it means that even if we have quite low amount of species, we can still have the emission spectrum. The problem is now that we have no idea of how much, for example, C2, excited C2 and excited carbon we have in our discharge. So we only have the idea that we have them, but we don't know how many. But apparently it's quite low.
And last questions that was also pointed out by Vasco was the use of the equation for temperature. I'm wondering why you are using this equation and not a simpler energy conservation equation.
Sorry, which equation? Well, I couldn't hear.
I mean, the equation of temperature. I don't remember now.
Okay.
You have an equation, a differential equation, but this can be done simply by an energy balance equation. So equalizing the energy you put inside, the energy that goes down, and what is inside the internal degrees of freedom, chemistry and so on, and the rest goes in temperature. Why you don't use this kind of equation? That I think is more accurate because it should include everything.
Okay. Okay, so I will probably, may I open the thesis and find this equation?
I tell you the number, just a second.
I think it's...
For the fast heating, you wrote an equation.
9 points.
I don't remember yet. I have to check.
Okay. This is this one.
I cannot find it. I mean, is the equation, I cannot find the equation, I don't know. Let me check if
I'm sharing the screen now, probably I'm talking about this one.
Yes, exactly. 9%, okay.
Okay, so why am I using this one instead of the, let's say, the energy balance?
Yeah.
Okay. Well, I was trying to use the energy balance. Well, first of all, this is the differential equation because the fact that the RG, which is the rate constant, is dependent on time. So the increase of the temperature at each time instant is also is not constant. So that's why we have to have we have to take into account the change of the temperature at...
yeah, sure,
yes.
I mean, but here you are saying that the only variation of temperature are due to reactions, while you have also the Georgy, for example, even if it can be small in these conditions, but you still have this. And I mean, you have elastic conditions, you have many things that can change the temperature. So why you just consider this equation? Because you can write the energy at the beginning of the step equal the energy at the end of the steps. And the you have all temperature and temperature. It is almost the same, but this is more general. And also the use of gamma here. I mean, you take an equilibrium gamma, as I see from the reference.
Yes, exactly.
And this can be different from the real gamma. one, there is the contribution of vibration, of rotation, of electronic states, there is everything inside. It's true that the temperature is not so high. What temperature do you use? If you arrive to, I mean, if you go above 1000, you have the contribution of vibration for sure. And this means that you have a higher value for the specific heat. And so the ratio approach is 1.
So when
This can be, you can have some differences in the gamma.
yes, yeah, that's true. And yes, we can have the difference of the gamma. So if we this is the equilibrium gamma, and then as we know, the vibration, well, there is a vibrational excitation of molecules, but first of all, well, the ratio of the vibrational excited molecules among the entire gas is quite low. It is well, less than, I would say, 5%. So it means that we are talking about the mostly, well, non-vibrationally excited molecules.
No, yes, no, I agree with this. But this term included. Gamma included. The one you are using, why you should use a gamma without vibration, because vibration is considered separate. That's what I'm saying.
Okay. Okay. Well, the gamma is well, yes, here it is without vibrations.
So equilibrium is not really appropriate in this case.
Sure. Yeah.
Okay, for me it's enough.
Mr. President, I'm sorry, there is a technical issue, the battery is low. Do you have a charger?
Okay.
Just 30 seconds.
Okay. Well, I haven't even noticed.
Just a second, I will prepare the issue.
Yeah, I was mentioning Georgy and Medici. I think that you will be the next. Okay.
Yeah.
Have few technical issues.
Okay.
I just please just wait 1 second. There, Georgy is.
Okay. So now it's perfect.
No.
No, it's not. Yeah. Here.
Yes, okay.
Okay, please go ahead.
So can I start? Yes. First of all, thank you, Georgy, thank you, Svetlana, for asking me to be member of this distinguished jury. I have to say, I have been reading the thesis with great pleasure, but because of the reasons why all the other members of the jury appreciated the fact that it is a combination of experimental and theoretical work, of modeling work. This is the only way to understand something that is very complex and mostly unknown to now systems. But also because I found many analogies with our work with nanosecond discharges. Many analogies and some differences, of course, but I greatly appreciate analogies because our system is somewhat different because we have not a tube in which the discharge is constrained and we import atmospheric pressure. So finding analogies is very interesting. But let me start first with technical questions. Just check if you can hear me correctly. Yes, can you hear me?
Yes.
Please. Okay. Couple of technical questions. First, about the fast heating essentially by energy transfer from electronically excited States to gas translation. I would like to ask you an opinion. How much do you think that the rate coefficients that you are using for these processes can be considered reliable? I apologize. I read this part many days ago, so I don't remember very well the references. I guess they were measurements. And your opinion about the reliability of these rate coefficients and the fact that maybe this process might be overestimated because, as far as I understand, you are supposing that all the energy of the electronic state goes into gas heating, into translation energy, while there could be, now I don't know the details, but there could be a transfer to other excited states of the collision partner that may radiate, for example.
Okay.
So please, your opinion.
Okay, thank you for the question. Well, the most part of the constants were measured experimentally in the previous works, even in the last century, and indeed what is connected to the gas heating. In fact, the difference of the energy defect, which was presented in the slide, in my presentation, it takes into account the energy defect which is common to the translation of degrees of freedom. But for example, let me show. For example, okay. The direction which is designated by the black curve, O1d plus CO2, well, here we have the excitation of vibrational degrees of freedom. So we not only have the gas heating, but we also have the vibrational excitation. The same calculations and the same assumptions were done for the rest of the reactions.
I see. It would be nice to design some experiments to see if you know that every kind of investigation, both experimental and modeling, relies on the goodness of rate constants. And given that, I agree with the result that at such low delays from the ignition of the discharge, it must be it must be this the process. But I think this is a field of further investigation to understand better this kind of energy transfers. And so do you think that this same result can be transferred to high pressure, to atmospheric pressure discharges?
Okay, so as for the atmospheric pressure discharges, we can't really ignite the capillary discharge, nanosecond capillary discharge at higher pressures. So it was found experimentally then that the fast ionization wave stops to propagate at the pressure of approximately 50 millibars. So in fact we lose this opportunity to have the specific deposited energy. And probably in your case, when we have the nanosecond repetitive pulse, at atmospheric pressure, when we have this memory effect, I think well, it should work nice. But at this point, well, you heat the gas, which has enough time to reply for the gas density has enough time for reply for the measurements of the temperature, for the difference of the temperature. So it means that we have to include the thermal dissociation of the CO2 as well, which it was not taken into account here. So this is the main difference.
Okay, thank you. Then let's go to another point. You made some reasoning, some deductions on the electron energy by looking at the emissions and at the energy thresholds of these emissions. But the underlying hypothesis in that case is that all those emissions are due to electron impact. So, have you, yes, okay. Have you any way to justify this hypothesis that all the emissions we are considering are due to electron impact? For example, in our case, we could see that the swarm bands were not due to electron impact, as well as, for example, in case of nitrogen addition to the discharge, the CN angstrom system was not due to electron impact. So, while other emission, we could see, for example, that they were correlated to their time evolution was correlated with the time evolution of the discharge current. So in some way we had some idea that they were due to electron impact. Have you any observation of this kind that justifies the assumption of electron impact?
Okay, thank you. Well, as for the UV doublet system and the FDB system, well, we see them in their first pulse. And so in the very first nanoseconds of the development of the discharge. So, well, it can be concluded that the excitation of these states is really due to the electron impact. So it means that the electron, the electron energy of some electrons is almost 20 electron volts. Then, as for the Swan system, we see that it starts to appear only in the second pulse. For example, if it was between the pulses, well, the appearance of the Swan band, for example, could be due to the collision of two carbons with M, C plus M gives to C2 plus M or something like this. But since we have the Swan band in this exactly on the time of arrival of the second pulse, so apparently it's due to electrons. But not necessarily due to the electron impact, but well, it's related to the increase of the electron density.
Because could you, for example, deduce something from the rotational excitation of the Swan bands, and see, for example, that it is not very high? Because in our case, we could fit the Swan bands with 6,000 degrees, so that was clear sign of some exothermic reaction causing the emission, not electron impact. So I see the Swan bands here. Did you try any fit of the rotational?
No. Well, I didn't try any rotational fit of the Swan band. Well, probably it would be interesting, but like the first clue of the optical emission spectroscopy was, of course, to understand which species are abundant. And then when I was adding nitrogen, it was necessary to understand to measure the gas temperature. And I'm not sure if the gas temperature is related to the rotational temperature of the Swan band. And the rotational temperature of the Swan band, well, as the parameter itself, it's interesting, but well, so far I'm not sure. Well, how can it be related to the other parameters?
I see. So then, can you conclude that the first pulse, in the first pulse, electrons are more energetic than in the second and the third pulse?
For sure, yes. Then the energy in the first pulse is the biggest among the values.
Right.
Yes.
Yeah. The same that we found in our case. So that's very nice. And now, okay, thank you for these replies. And now I have some. As I told you, in our case we have not a capillary. In your case, the volume is constrained capillary, and the capillary can have a role, for example, in the temperature, in the gas temperature. I mean, for example, before doing this, have you observed some deposition of carbonaceous films on the capillary or not?
If I have observed some deposition of carbon on the capillary.
Yeah.
Okay, so I wouldn't say that. Well, I observed something. So probably this process happens very in a very slow way. We observed that like after 2 years pause of the experiment between the experiments in the thin capillary, well, we had to change it. So probably, it was somehow influenced by plasma. But my idea that, probably carbon which is formed in the discharge is not a solid state. It's more like a vapor, which then recombines back to CO2. But probably it's really behaves like a vapor, which is simply is effluent from the capillary to the exhaust.
I see. I see. Okay. Now, because there could be a simple way to see this. For example, if after a long usage of the tube with CO2, you may try to switch on a discharge without CO2, for example, in pure nitrogen, and see if you observe CN bands, for example. If you have some carbonaceous deposit and you make a pure nitrogen discharge, you may observe a CN bands, for example. But anyway, this was a curiosity because if you have some deposit, this could influence the appearance or not of emissions, even in the first pulse. Anyway, so back to the role of walls, let's say, in the physics of the discharge. Do you observe a significant heating of the walls?
Okay. Yes. We didn't measure the temperature of walls, so we didn't have any quantitative measurements. But when we were doing the measurements of the dissociation fraction by FTIR at high pulse repetition rate, for the repetition rates which are designed by the orange rectangular, we had the significant increase of the temperature, which was enough to melt the supports, the plastic supports, yeah. And that's why we had to change the capillary.
that's a point, because, of course, I have seen that in your modeling, you do not consider the walls. And as far as I understand, this is mainly because your modeling is restricted to the discharge period, let's say, it doesn't go at delays larger than, let's say, 1 microsecond. Because it is interesting, it would be interesting to see how the gas temperature evolves after the pulse, and to see how, if there is a fast cooling of the gas that can in some way freeze the dissociation and avoid the back reaction, or if this cooling is slow, and certainly this can be greatly influenced by the wall temperature. So that let me understand well, are you really discarding the walls now just because you are looking at modeling just in the discharge period?
Yes, so in the chapter 4 I give the estimation of the, let's say, of the electron diffusion to the walls. Well, it's about 10 to minus 4 seconds, so almost 10 to minus 1 milliseconds. And we were really taking into account the behavior, well, the plasma kinetics on the discharge axis at nanosecond time scale. And of course, yes, well, it will be very interesting. It will be very fruitful continuation of the work to extend this plasma model to the late afterglow.
I see that this is something that that might influence the final result of the dissociation, because you may have a very high dissociation in the discharge, but then if the gas heating is very high, probably you may have an important back reaction that in some way limits the good dissociation result. Anyway, I am not sure. Yes, I have another question on the figure in which you showed the time evolution of concentrations. One of the last figures, I think.
Okay.
And in the thesis, yes, this one. I don't see here because in the thesis you sent me figure 911. There is also there is a difference, because in figure 911 that I have here, there is the purple curve, which is labeled as CO. But in this, I have a label here with five species: CO, COA, CO2, O3P, O1D. But in this figure, I don't see CO.
Okay.
I don't know which is the correct one, but if I have to interpret the CO curve, it looks like what here in the presentation it is labeled O1D. I don't know what is the correct one, but according to the figure I have on the thesis, CO between the pulses decreases a little bit. It is the same. So please tell me what is the correct one.
Okay.
What is CO?
Both of them are correct, in fact. The difference among the one which is given in the current presentation and the first version of the thesis is the absence of the O1S curve in the O1S curve in the thesis. It was caused by the fact that well, the mechanism was actually suggested and discussed by another author, by Dr. Nikolai Popov, which asked not to publish this mechanism and the details of the mechanism before the submission of the article. Now the article.
Sorry, excuse me. Sorry if I interrupted you, but in the figure in the presentation, where is CO? I have CO in the thesis, but not in this figure.
CO, you mean the CO,
carbon monoxide.
Yes, you mean like the
ground state. The ground state, I mean, not
okay. Because here, well, I showed this just because, well, I want to show the role of the excited states, and not all of, well, not CO.
I see, but I have CO here. Is it correct, mine?
Yes. Yours is correct.
Oh, okay. So in this figure, I see that after the first pulse, after the second pulse, and after the third pulse, CO at the beginning increases, then decreases a little bit. So somewhere else in the thesis, you state that you are not considering the back reaction CO plus O that gives back CO2. So why CO is decreasing?
Okay, so probably it's just it's a misunderstanding. Well, in fact, CO here, which is designated by the red curve, is the CO in the ground state. But we also have the CO vibrational states of CO, which that's why. Well, if we take into account CO plus COV, well, it should be constant.
I see. I see. Okay. Okay. Thank you. And then I have the final $1 million question. Since, of course, we all like to discuss about molecular processes, about discharge processes, and so on, but in the end, we would like to save the world by limiting the greenhouse effect and saving enough energy, at least to make Zoom calls like this one. And so your system is your system suitable for a technological application? Or do you think that you have anyway switched to some atmospheric pressure treatment? For example, if you go to an investor, an engineer who is willing to invest in green technology, he will ask you, but okay, what is your energy efficiency? Does your energy efficiency take into account the energy consumed by the pump, for example, by the vacuum pump? So do you think that this system at low pressure, relatively low pressure, can have a technological application, or are you making important fundamental studies to understand the kinetics, to understand the device, but a true technology should switch to atmospheric pressure? What is your idea?
Okay. Well, this is a very interesting question. Well, first of all, unfortunately, the capillary discharge can't really work at atmospheric pressure, since, we lose this benefit of high specific deposit energy. But, I can defend a little bit this capillary discharge, that it can probably work on Mars, since, the pressures of the atmosphere of Mars is a moderate pressure. And, I remember there is a publication where it's possible to combine several capillaries, well, not only one, but well, make a set of them, and well, this can be an enhancement of the dissociation yield. I mean, like, well, we can produce more CO2, or we produce more CO at this the same amount of time.
So you think that there is a technological interest in this?
I think, yeah, it's more interesting for, yeah, well, for moderate pressures. I think it can probably work in, yeah, in Mars. Well, since it provides a very good energy, dissociation fraction, well, normal energy efficiency, and well, if we play a little bit with the parameters, well, it can have a future.
Okay, okay. Thank you. I'm satisfied. For me, it's okay. Thank you, Georgy.
Thank you, Georgy.
And so next is Olivier Guatella.
Thank you, Mr. President. Thank you, Georgy, and thank you, Svetlana, for inviting me to this jury. I want to say that I really enjoy your presentation. From my point of view, you made it even more clear some parts that were maybe not so well phrased in the manuscript, and the presentation was really nice, really clear. I enjoyed it. Also, it was a pleasure to work with you on the FTIR data. I have, of course, many questions ready for you. Until there is a question of Giorgio, I thought that I had plenty of questions. I have now much less. But still, I have a few questions to ask you, and in particular, in the same way that for the modelers, you can have the model as good as you want. It always depends on the input parameters that you are using and the assumptions that you do for the model. I have to admit that also for experiment, there is no such a thing as a perfect experiment, and that it's important to be aware of the limitation of any diagnostic technique. So I was not clear, because I've never used this technique, I was not clear on the limitation of the capacitive probe measurements. And I would like to come back a little bit on the field value that you obtained from it. So if I understood well, first question, can you make a bit more specific the geometry of the capacitive probe, in particular the area, the surface of the probe itself, and the distance to the capillary tube?
Okay. So, well, unfortunately, I don't have the slide. Okay, so the capacitive probe, it's let's say it's a surface which interacts with the capillary. Has the area of about 1 micrometer square, not 1 millimeter square, and the distance between this sensor, let's say, and the capillary is around 1 centimeter.
Okay, so from what I read in the manuscript, so you did a calibration, which is very nice, with a copper wire or foil.
It was a foil, yeah.
So in which you apply a voltage pulse, as it is a perfect conductor, well, almost perfect.
Yeah.
The transmission of this wave through the copper is maybe not the same as the fast ionization wave passing in front of the probe. My wonder is to which extent the probe is sensitive already to the field when the ionization front is approaching, and how much is still sensitive to it when the front is already passed, and how does that affect the shape of the signal you get from the probe. That's why I was asking about the distance, because I guess if you would change the distance to the capillary, maybe that would change the response of the probe.
Okay, so yeah, it means that, well, we have the distance, and we have to calibrate the probe at exactly the same distance. Yeah, so yeah, otherwise we change the amplitude and we change the response time of the capacitive probe. These are the parameters which are found during the calibration. Then, well, it is essential to remember that we have both, we have a transversal electric field and longitudinal and a transversal electric field. And the capacitive probe is sensitive to the transversal.
Okay.
Yeah.
You mean
The longitudinal.
okay, and not the transversal one.
No.
So why is that? Can you explain?
Well, because it's it develops like this, and well, since the capacitive probe works on the is moved along the distance and not like this, so well we can't distinguish the transversal components.
Okay, so you are not disturbed either by charge deposition on the dielectric wall. So this time, after your ionization wave passed, you probably have charge deposition on the wall, which would result in a DC component, I guess, in your output signal. But how would that affect, for instance, the next pulse?
Okay, so like the measurements with the capacitive probe were done in the thin capillary, so we expect that the electron density, the additional electron density, will flow to the low voltage electrodes. So, and it means that before the arrival of the second pulse, the discharge tube will be clear from this discharge.
Okay. Can you see that from your probe signal by any chance? Or?
Well, we didn't have any constant electric fields, for example.
Okay.
Between the pulses.
Okay. Thank you very much. So related maybe to this field question, when you show the electron density profile deduced from the N2C emission, I found the discussion on the quenching rates and the justification that you populate by direct electron impact excitation very good. I'm not discussing that. I was just wondering, okay, you see a radial profile and you relate it directly to an electron density profile. But could that be an electric field profile? And in particular, you mentioned that there is not only the actual electric field, but there can be a radial electric field. To which extent this could affect the profile of the emission that you monitor?
Well, okay. Well, as far as I understand your question, is whether this this radial profile is related to the electric field.
And
so the transversal.
It's both electron density and electric field, right? Because you need to excite the N2C, which will depend on both.
Yes, it depends on both. But mostly it depends on the electron density. It's related to the electron density. And the electron density, for example, is not related to the electric field itself. For example, it is still non-zero in between the pulses. Despite the fact that we have a zero electric field between the pulses. And also we have the ambipolar diffusion, and we have the free diffusion of electrons and the diffusion of ions. And I wouldn't, let's say, dare to claim that it's the radial profile of the electric field.
Okay, thank you. Georgy already asked you this question, so it's maybe more of a comment now. But can you show your energy diagram in which you show the different level of the different species?
Sure.
So, okay, it's maybe more a matter of taste than anything else, but as Giorgio said it already, to show it in that way suggests that all the transitions you are mentioning are all due to direct electron impact excitation from the ground state of the CO2, which from my point of view is a bit misleading, especially for the CO band. Because as far as I understand, you see, for instance, the third positive system only at the, I forgot, second or third pulse, which would make sense because you need first to form the CO and then excited by electron impact from the ground state. At least, can you explain why this would not be the explanation to see for me at the third pulse?
So why do we see the third positive system only at the third pulse?
Yes.
Okay, because it's okay. So because in the first and the second pulse we have the fourth positive system, which is overlapped with the third positive system, and probably the
you can distinguish them. You have enough spectral resolution to distinguish them. So.
Okay. Let's take a look. Yes. So, for example, this is the fourth positive system in the first pulse, in the second pulse, and in the in the third pulse it's
and then you see it clearly here.
Yeah.
So my feeling is that you don't produce the third positive system directly by electron impact on CO2 dissociating.
It can be from pool reactions as well, but we didn't study this. Pooling reactions.
Okay, my wondering was more if you have already produced enough CO from your first and second pulse,
okay,
then you shoot a new burst of electron that can excite this CO.
Mm-hmm.
So you can just excite from the ground state CO, right?
From CO, from the ground state of CO, probably from COA.
In which case you would need, or from COA.
Yeah.
In which case you would need, if you shoot on the ground state, you need only 10, a bit more than 10 electron volts.
Mm-hmm. Yeah.
And then my next question would be, can you go back on the energy diagram? And that's actually a question I have in other discharge, so that's why I would like to have your feeling about it. In fact, if you would place your CO level from the ground state of CO instead of from the CO2, you would have the CO small b and CO large b, both between 10 and 11 eV. So basically, one could consider that if you excite them by electron impact on the CO ground state, they should be excited by an electron having more or less the same energy. But you don't see the Armstrong and you see the third positive system.
I see the Swan system, not the third positive system.
Instead, in the third pulse, you see the third positive system. Mm-hmm. We have just seen it.
Yes.
But you don't see the Armstrong. So that's something I wonder, we have seen that in other discharges, and that's really an open question. I don't have the answer. I just wanted to have your feeling about why you would see the third positive system and not the Armstrong band, while they can be excited both by basically the same electrons.
Well, I was thinking a lot about this. The first thought which comes to the mind is that, well, Armstrong band and Swan system are, well, they overlap. Well, this one system, for example, can be, I guess, well, this state has, C2D has a quite long lifetime, and it means that, well, even, for example, if the electron temperature is, decreases in the third pulse, in the afterglow, the C2 Swan band still, well, we can see it. And this while, it will still dominate the Armstrong band, which overlaps with this one system.
Okay, maybe it's just a matter of relative intensity of the event.
Yeah, the relative intensity and the lifetime of this one system.
Okay, then maybe it's getting late, so I will not torture you too long. I will maybe just ask you one last question that popped up into my mind when you were discussing that you did not take into account the negative ion in the kinetic scheme, which I believe is perfectly fine for modeling just one pulse. I was just wondering if you think you had to consider this low electric field in between pulses of 20,000. And with such low electric field, maybe you could favor attachment. So I was wondering, in between pulses, to which extent the attachment and the production of negative ion could be relevant, and at the initiation of next pulses, be an important source of electron to reignite the next pulse.
Okay. So the question is whether like this fictional electric fields can facilitate the attachment. Well,
yes, and therefore to which extent negative ions could be responsible for an additional source of electron when you, on the contrary, reapply a strong electric field that could get back this electron from the negative ion.
So yeah, the detachment process.
Yes, detachment.
Oh, well, I didn't take this well into account because the sensitivity analysis was done, of course, without the fictional electric fields. It was done in the pulses themselves. Then, we were planning to make an additional series of modeling experiments when we will have this burst of pulses with nanosecond pulses, and then we will have the relatively low, probably constant electric fields, or probably tens of thousands, in order to facilitate the vibrations. And so far, well, we can take a look what happens if we combine the electronic excitation in the first microseconds, and then the afterglow, the vibrations. And well, we didn't think so much about the attachments, the detachments, but well, it would be probably also a good point to do so.
Okay. Well, thank you, Georgy, once more. Congratulations.
Thank you.
Thank you, Olivier. I propose that I ask a few questions and then I let Svetlana give the final comments and remarks.
Sure.
That's okay?
Sure.
Okay.
Yes.
So the million-dollar question already got asked, so I'll ask some of the 50-cent questions. George, when I was reading the thesis, the part that surprised me the most was really looking at the two capillaries and saying that we're going to say that they're basically the same. Just for me, from an electrical standpoint. So for me, the one filament, sort of the entire filament becomes a part of the coaxial cable, right? You have once the discharge is there, I have my metallic shield that goes around it, and so then it continues as another coaxial system. Whereas in the FTIR setup, it kind of looked like I had my coaxial cable coming, and then the ground sort of took another path. And I was wondering, in reality, in the system, does it still look a little coaxial with an opening for FTIR, or is it more like a true cable system with the ground following a second line down to the other end of the
Okay. Okay. I'll explain. Thank you. So yes, indeed, in the thin capillary, the discharge itself is like the continuation of the central wires of both their coaxial cables, and in the FTIR, well, in fact, the shielding was connected to a copper foil, and the copper foil was stuck on the outer surface of the capillary. So it was like this. So along all the length of the capillary.
sort of like a strip line along.
Yes, exactly. It was a metallic foil strip.
Okay, so this would kind of affect how the breakdown happens, because in one case the field lines from the center kind of go outwards to the shield, and in the other case you kind of you see sort of a half or less. Could this affect how the breakdown occurs? Does this matter for a fast finite symmetrical on one side, or sort of just the two strips? Does that matter for a fast ionization?
Oh. Actually, well, I haven't thought about this at this point of view. Well, well, we didn't try to stick like metal foil on both sides of the FTIR capillary, and well, of course, well, the main difference is the fact that the fast ionization wave is reflected from the grounded electrode, and well, then we have in fact an overlap of incident and reflected ionization waves. But since we actually, well, we didn't have any ways to distinguish, to resolve the fast ionization wave, well, we can't even, we can't say anything, well, and we can't compare. But probably, well, I would say, well, there should be an influence of this asymmetry.
Yeah, I don't intuitively know. I think already the reflection, now the impedance mismatch when the wave goes from the coaxial cable to your system, and already the impedance mismatch between those two, between those coaxial and some of those strip lines, will probably affect how much that first reflected pulse goes back, the one that goes back to the source. So I thought maybe the magnitude of the reflected pulse could already give you some hint on how the system looks before the lights. Okay, I don't want to, this is more curiosity. You also said that for your, when you did the calculation of current and voltage, more calculating the voltage of the line from the back current shunt, and you said that you get one from the other because connecting through the characteristic impedance on the cable. And that was sort of even in a simpler form of the thesis, you just said we can measure the voltage because of the back current shunt. Sorry, the current, basically the current, and that you get voltage propagating because of the impedance. So that assumes that the back current shunt has an identical behavior in impedance to the rest of the coaxial cable. Was that true? If you just do a measurement with just the back current shunt and nothing else, do you just see the pulse bouncing back and forth, or is there another reflective pulse that comes off?
No. So it was exactly so. They were, well, back current shunt is the combination of parallel resistors which are inserted in the shielding of the coaxial cable, and well, we didn't see any reflections. And if we saw the reflections, so it means that well, we had to refabricate the shunts.
Okay. And just one last for a bit of an outsider here. I found that throughout the thesis there's a lot of different time scales going on. And sometimes I had to go back and refresh my memory as to, we're talking about the time between the pulses that are being reflected or between subsequent pulses from the pulse generator, and then how do the different different decays and different compare to those. I thought for just educational purposes to have sort of the, when you talk about the different species decays and the residence time of the gas in the chamber and the time that the pulses take up and so on, and the time of the fast ionization, it would be neat to see all of those timescales sort of graphed together so that you sort of separate out the processes in our mind. Just someday you'll have to do another presentation on this probably somewhere. It would be a nice pedagogical tool to sort of get all those scales into mind, especially when it came to the discussion about the residence time of the gas versus these different processes. There is where it sort of moved in hand. And those are my 57 questions. I'll now pass the floor to Svetlana to make final comments.
Well, thank you very much, Georgy, and my comments should be not about scientific part of the thesis. Can you hear me? people who are in Zoom? Can you hear me? Okay. So my words should be not about scientific part of the thesis, in spite of the fact that I liked very much the discussion and your questions. But, well, maybe next time I can answer part of them in my way, or Georgy can answer in his way. And actually, from this discussion, which lasted almost 2 hours, I can conclude that what presented my PhD student was interesting for you guys. Because if not, you would not continue the discussion for 2 hours. And why I'm very thankful to Georgy, because when he came for his PhD thesis, we have never even tried to ignite the nanosecond discharge in CO2. And as Georgy mentioned in the introduction, we knew at that time that nanosecond discharge is an efficient tool of dissociation via electronically excited species for, let's say, oxygen in air. And so I told him, okay, why not to try and not to see what will happen. And actually we started almost in parallel with Georgy's experiments at atmospheric pressure plasma. And finally, I'm happy to see that Georgy was able to combine in, I find, quite elegant way, the experiment and the numerical modeling. Yes, I'm really sorry, Vashko and Gian-Piero, this was numerical modeling for support the experiment. Okay, this was not a self-purpose of the thesis. But still, my personal opinion as scientific supervisor, we have this result exactly we wanted to have. We have the tool which helps us to understand what happens in the discharge and to relate what we measure by backcurrent shunt, what he measures by optical emission spectroscopy, even by FTIR, with what we see in numerical modeling. And actually, strangely, for Georgy, this coronavirus period where he was not able to perform his experiments was very productive in the sense that he really developed the modeling. What also I wanted to say is that during thesis, Georgy demonstrated his very nice skills for collaboration, because part of experiments you saw this FTIR were done in collaboration with Olivier, and part of numerical modeling, in particular electronically excited species for fast gas heating, came to the model due to collaboration with the Lea Kappa project with Dr. Popov from Moscow. So finally, due to hard work of Georgy both in experiments and in numerical modeling, we have this very nice and very certain step in nanosecond discharge at moderate pressures in CO2, and we can continue from here to get again more interesting results. And I'm really happy that Georgy was this PhD student, a person who was able to link experiments and numerical modeling together. That's my point. Thank you very much for your participation today, and thank you very much, Georgy.
Thank you, Svetlana.
Okay. So I believe that now is the moment for deliberation.
Exactly, and how we do this, we ask people to leave the room, and we will stay only jury people.
That's for mispronouncing your name multiple times during the defenses. But on behalf of the members of the jury, we would like to congratulate you on your successful defense of your PhD and your agreement that you should be issued a degree of doctoral PhD from the AI comparison program. Bravo. Round of applause. congratulations. There will be some minor changes to the thesis according to the complex of the jury. And that is also, please, on behalf of us, good luck. And you're allowed to have a poll.
Sorry?
Are you allowed to have a pool?
People, yeah, well, there will be food as well in there. Probably in
Excellent.
20 minutes.
I wasn't sure what the rules were this week, so please enjoy the poll.
May I add, since I am far away, let me toast from here. Even if only for 1 second, can I see your face? Thank you very much.
Thank you. Thank you so much for participating in the jury and for reading the thesis and for finding these excellent questions which will help to improve the results and improve the development of the problem. Thank you.
And I think I'll repeat the comment, a few of the comments that were made, is that the level of difficulty, the questions that were asked by the jury were a very positive reflection on your command of public speech. I think that was noted very quickly that this became a very nice professional discussion. I particularly enjoyed this back and forth. So, without further ado, congratulations, and go take a breath.
Okay.
Right.
Pleasure, yes.
Thank you very much.
Okay. You can dismiss.
I hereby adjourn this jury.
Okay.
Okay. Thank you very much. So